Hello friends, so today we will take up tutorial 3, which is basically dealing with MATLAB code for generation of Walsh-Hadamard code, and we will check its correlation properties in order to establish how these kind of codes are useful for spread spectrum communications. In fact, this tutorial is the beginning of the series of tutorials where we will discuss MATLAB codes essentially. The first two tutorials in fact were dealing with certain numericals on DSSS and FHSS. So from now onwards till I think tutorial 8 we will be dealing with MATLAB codes and performance evaluation of systems, and we will try and gain an insight into how to simulate spread spectrum systems and evaluate their performance. So I assume that most of you are familiar with MATLAB, or at least certain aspects of MATLAB, because that will prove useful as a prerequisite to our discussion. So the objective of this tutorial is to generate a Walsh-Hadamard matrix, and the rows of this matrix will be corresponding to Walsh-Hadamard codes. We will check a periodic autocorrelation property, in the sense that we will choose a given row of this Hadamard matrix and we will test its autocorrelation property. We will plot it and check whether it follows any trend, and we will also check the cross correlation for a given pair of such codes. So we will choose any two rows of the Hadamard matrix and we will check the cross correlation property of these two codes. So that's the idea. A periodic, because we will not assume that the codes keep repeating, but we will take only one instance of the code and we will check the correlation property. So a periodic cross correlation equation can be expressed using this relation. So we have cross correlation term which is denoted by C cross, and it is between two different codes. So therefore we denote the codes by the notations M and N, and as we know that correlation has to be plotted versus lag over the shift. So we denote the shift by L. We have the definition such that for all positive lag values or shifts up to n minus 1, because this is L lesser than n, so we have a definition whereby we keep one code as it is and we shift the other code based on this index. So for all positive values we will have a shift in one direction, and for all negative values we will, that is for all negative values of lag, we will shift in the other direction, and we will check as to what is the corresponding product of the code values, and ultimately we will sum it over the product values. So this is a well known definition of correlation. I will try and show it to you with an example in the next slide. So it turns out that the values of this cross correlation term for this lag will exist, as we can see over here, from on one hand, that is on the positive side, it will exist from 0 to n minus 1, and on the negative side, that is for negative shifts, it will exist from -1 to minus n minus 1. So otherwise the value outside this range is equal to 0, which is essentially the meaning of a periodic cross correlation. So a periodic is because of this reason. We are going to test the property. The codes do not repeat themselves, just that once the overlap between the codes is over, then the value of the corresponding correlation term turns out to be 0. So that is the significance of the correlation being aperiodic. The autocorrelation term is just a special case of this cross correlation definition. So autocorrelation is nothing but checking the similarity between the same code, that is a code with itself, that is just a shifted version of the same code, and so therefore now the indices m and n are the same now because it is the similarity with itself. So we have only one index k, and we check the correlation property of the code with the shifted version of itself. So we assume the n length code, and specifically small c k superscript k subscript I denotes the ith sample of the kth code. So this is the notation that we are going to follow. So a fairly simple definition to begin with, and let's see what kind of a matrix is a Hadamard matrix. So as we see, we have Hadamard matrix which can be of a given size, and I think this has been dealt with in a previous lecture, so I am not going to get into it. But generally, whenever we have a Hadamard matrix, the first row of the Hadamard matrix will be of all ones, but here we see that we have a special case where the first row is not all ones, but it is a particular sequence. This of course is a special case, that is only known case of a cyclic circulant Hadamard matrix, but other than that, in general this row will be all ones, that is the first row, and it will not be used as a spread spectrum sequence because it serves no purpose. Basically we need a kind of a pseudo random sequence, but this is a sequence of all ones. So if we multiply it with data bit, there is no change in, or there is no spreading essentially that occurs. So usually this first row is a redundant row, but then there are other properties which are of interest. So to begin with, all rows will have autocorrelation values. That is basically, as I said, autocorrelation we take the code which is a row of this matrix, and we will try and shift, or rather try and find out the correlation between that row and a shifted version of itself. So at 0 lag, that is at autocorrelation equal to 0, we will have a multiplication of this, each of these bits with itself, and summation over it. So it is quite apparent that if for 0 lag, we will end up getting a value of autocorrelation which will be equal to the length of the code. For example, in this case, the length of the code is 4, so autocorrelation at 0 will be equal to 4, and in this case at 0 it will be equal to 8. Now as we shift the signal, what will happen is we will start getting certain values of autocorrelation, and that is what we intend to plot and analyze. As far as cross correlation is concerned, the idea is to multiply two different rows or two different codes, so to say, and then multiply it element by element and then sum it up, which will give us the cross correlation. So we will also see as to what peculiar property the Hadamard set of codes follows. In fact, if you just straight away look over here at cross correlation value across, that is between any two codes, at lag 0, that means without shifting it, will straight away be, this product of this will be equal to -1. So this product gives you -1, this product also gives you -1, this will be +1, and this will be +1. So take any other two rows as well. For example, we take these two rows, so we see that this is +1, this gives us -1, this again gives us +1, this gives us +1, this will be -1, this will be -1, this is again -1, finally this will give me +1. Of course, I am assuming that plus here and minus here stands for +1 and -1 respectively. So what we notice is that the summation of this, if I sum over all this, then the result is equal to 0. Similarly, here also we can see that there are 4 ones, 4 minus ones, and summing up over this entire range of product values gives us 0. So one thing is quite apparent, and you can try it out across any two rows from this given Hadamard matrix, and what you will realize is that cross correlation at 0 is equal to 0. So we see two important things that we need to establish over here. One is that autocorrelation at lag 0 is equal to the length of the code. So this was discussed first, and the cross correlation at lag 0 turns out to be equal to 0. So these are two properties that we see straight away, and the rest of the task now is to verify this and also find out autocorrelation and cross correlation for various values of lag, so and then plot it. So let us have a look at it, but before that let us see the program that we use in order to plot these values. So this is the first MATLAB code in the series of tutorials for implementation of spread spectrum system. So I'll be a little bit more comprehensive in my explanation. So we first declare the length of the code and we store it in a variable. So in this code we have chosen a length of 8, and we generate the code matrix using the function Hadamard, which is a library function in MATLAB, and it takes a parameter of length. So if we specify length, it will generate a matrix which will have the number of rows equal to the length. So in this case we will be in a position to generate a Hadamard matrix, that is a matrix with Walsh-Hadamard rows corresponding to different Walsh-Hadamard codes, except the first row, which I said is all one row, and in this case the matrix will have a I have the number of rows equal to 8. So we assign a value of which is basically an integer, and we have a variable which we call as a code index. So we can actually assign a specific value to this variable, and we were going to make use of this in order to select a certain row from this Hadamard matrix. For example, in this case we have set the code index to 6, which means I will be choosing the 6th row of the Hadamard matrix in order to plot either my autocorrelation or my cross correlation, as the case is. So In line number 14, we see that we use another inbuilt MATLAB function which plots the correlation of its argument. So if there is only one value of argument given, then it will plot the autocorrelation, and when we have two values or two arguments, then it will plot the cross correlation between the two. So in the first case, we are interested in plotting the autocorrelation of any given row, that is any given Walsh code from this Hadamard matrix. So we choose that as row number 6. You could change this and try out the plot, but in this case we choose the 6th code. And further, for cross correlation, we need two codes, so we choose row number 3 and row number 6. So make sure that code index should not be 1, because as I said, the first row is a row of all ones except a special case, but otherwise it's all ones. So we find the cross correlation by once again using the same function, but now we have two arguments. So that is choosing the row number 3 and row number 6. We need to plot the values of this autocorrelation and cross correlation. So therefore we need to assign a index, a time index basically, or a shift index to be more specific in this case. So we do that by generating a x-axis index from length autocore, which will give you the overall length of this correlation. So we know that if I have two entities which have lengths of m and n respectively, then the correlation length will be m plus n minus 1. So therefore that will be the length of this auto and cross correlation results or vector. And then we stem, which is a discrete plot of this autocorrelation versus the shift index, which will be on the x-axis. So these commands from 25, or rather from 25 to 31 are in order to plot the figure. So let us see what the plot yields. So for code number 6, which we had chosen, the autocorrelation function looks something like this. As we can see, at shift index 0, this is shift index 0. So for shift index 0, we have a value of 8, which is equal to the length of the code. That is what we had established in the previous slide, that autocorrelation at shift 0 should be equal to the length, and then the rest of the values of autocorrelation will depend upon the code that you've chosen in order to. So all codes will not have the same autocorrelation plots, as you shall see, but the importance of having a good autocorrelation property, and when I say good autocorrelation property, it means the at lag 0 you should have a high magnitude of autocorrelation, and that should gradually decrease, or rather should be very small for other lags as far as applications such as synchronization is concerned. Because what we are trying to do is, in synchronization is we are trying to find out or synchronize two entities, and so for the desired signal, if you in a spread spectrum system, as you are aware, if you want to synchronize the incoming signal with the code that is being locally generated at the receiver, then usually we compare the autocorrelation at lag 0 with some threshold. So in order for us to meet that requirement, the autocorrelation at lag 0 should be as high as possible. On the other hand, sometimes it is also desirable to have a high value of autocorrelation at 0 and a reasonably high value just after 0 as well, because sometimes in cases of loss of synchronization, the second value also is important in order to detect the signal and synchronize it. Nevertheless, usually the case is that we need a very high autocorrelation at 0 lag and low values around it on the positive and negative side. Usually such codes which give you such good autocorrelation properties, as we are aware, are we have the PN sequences. You might have learnt about maximal length sequences, pseudo-random noise sequences, and also codes such as Barker sequences. So they are have codes which have pretty good autocorrelation properties, but then the catch is that usually it is seen that it's a compromise between auto and cross correlation properties of a given set of codes. So a set of codes which have good autocorrelation properties, it so turns out will have bad cross correlation properties and vice versa. So it's always a trade-off or a compromise, and it depends upon what kind of application these codes are used for. On the other hand, let us look at the cross correlation properties and of code 3 and 6, which I think we had chosen for the program, and we straight away see that at lag 0 we have a value of 0. So that is what I told you. You can try it out with other codes as well. This particular feature will remain the same, property will remain the same. And now we notice that as we shift one of the codes, like in this case if we keep code 3 the same and we shift code number 6, for different lags we end up getting values. So sometimes it is 0 and at other times the value turns out to be 1. So this is a very interesting property of Walsh-Hadamard codes. It's not always necessary that this will be the pattern of cross correlation between any two arbitrary codes. The pattern may change, but two things you will notice will remain the same. One is that the cross correlation between any two arbitrary codes at lag 0 will be 0, and otherwise it may either be 0 or it turns out to be 1 or minus 1. The interesting thing is it doesn't go beyond this value, and that is applicable to any two arbitrary set of codes chosen from the Hadamard matrix. And this is important because what we desire is also, and this is important in a multi-user environment where there is going to be a lot of interference, let's say, is what we desire is that for good interference rejection properties, or in order to discriminate between different users, that is a desired user and then unwanted users, the codes should assigned to these users should be orthogonal, and moreover it should have very good cross correlation properties. And when I say very good cross correlation properties, it means it should have a 0 value at lag 0, and it should have low values around this 0, that is for positive shifts and negative shifts. So here there is some kind of a cap on those cross correlation values. We see that they don't go beyond 1, which is good, and so this is a pretty good code to be used both for synchronization as well as in a multi-user scenario, because it has fairly good autocorrelation properties. I wouldn't say it's extremely good, because generally for synchronization, as I said, we use PN sequences or Barker codes. So, but definitely it has fairly good cross correlation properties, which can be used for multi-user spread spectrum communications. So let me wind up by showing you another example wherein we change these codes. So we see that the autocorrelation function for code number 5 looks something like this. Now we see straight away, let me go back to the previous slide, that for code 6 it's different. So it's not necessary that all codes will have the same kind of autocorrelation function. So you can change the value of this code index and try and plot the values for different code indices. That is, you can try and plot autocorrelation and cross correlation. We see another example where we have codes 2 and 5, but again this plot is different from the plot for cross correlation between 3 and 6. However, the features remain the same, and by that I mean that autocorrelation at 0, it turns out, is equal to the length of the code. Cross correlation at 0 lag again is 0, so those properties remain the same. Also, cross correlation doesn't exceed 1 and -1, as you can see. So these are the peculiar features or properties of Walsh-Hadamard codes that we in this tutorial try to understand, implement and plot. And just to summarize, codes with good autocorrelation properties like PN sequences, Barker sequences can be used for synchronization, whereas codes with good cross correlation properties, like in this particular case, can be used in order to discriminate between multiple users in a spread spectrum communication system. So this concludes tutorial 3, and in the next tutorial we will try and make use of these codes, and specifically the Walsh-Hadamard code, in order to evaluate the performance of certain spread spectrum modulation systems. So in that sense, this tutorial assumes importance, because we are going to make use of these codes throughout the remaining tutorials for generation of bit error rates, specifically for performance evaluation of spread spectrum systems. Thanks a lot.